engineering department, and has been such a great collaborator with the MIC, and we really appreciate his engagement and partnership with us. And so we're very happy to have him give a talk today on some of his research that's focused on TEM-based orientation mapping and strain mapping. And so Kelvin, I'll let you take over.
Thank you, Kristen. All right. Thank you very much for the opportunity to share some of our research with you today. My presentation title is TEM-based orientation and strain mapping. The work we do, they are generously supported by NSF, DOE, and AIL. Before going to the details of the TEM-based orientation mapping and strain mapping, I want to quickly just share with you what kind of research we do in our group. A lot of the results I'm showing here, they were generated at MIC using the TEMs in the microscopy imaging center. First, we do regular TEM imaging. In the first example you see here, we have a nanocomposite material. We do regular TEM. We also do regular STEM. The first micrograph you see is a HARDIF STEM image. HARDIF is high angle annular dark field image that highlights the Z contrast. So if a component in the material has higher atomic number, it will appear to be bright. From this micrograph here, you can tell there are two phases present in the material. We also can do chemical mapping using EDS. So there's titanium and tantalum present in the material. So you can see one phase is rich in titanium, the other phase is rich in tantalum. So that gave us the capability to not only look at the microstructure of the material, but also the chemistry of each component. In addition to regular TEM, STEM kind of imaging and spectroscopy, we also do a little bit of tomography. The work was done by my student, De Xing. What you see here is a shape memory alloy with precipitates dispersed through the volume in the material. What De Xing did was he acquired the HARDIF STEM image at every 2 degrees. So you can see a movie here. By tilting the specimen inside TEM, you'll be able to create a 3D model showing the morphology, size, as well as distribution of those nanoscale precipitates in this metallic, in this alloy system. We also do a little bit microscopy technique development. In this example on the top here, more specifically, one thing we're trying to do is something we call correlative microscopy. For correlative microscopy, we're trying to combine more than one type of microscopy techniques together to help us learn more about the material. The 2 micrographs you see on the left, those are the EBSD maps we acquired at MCF. What EBSD tells you is the crystal orientation information. In the example here, we also know the loading direction. So for each crystal here, we can calculate something we call Schmidt factor of individual grains. By knowing the Schmidt factor, we can predict what kind of deformation mechanisms should be activated. Then what De Xing did was he did electropolishing of the material. The center black or dark region is actually a hole, so there's nothing here. Then around this perforation, around this hole here, the material is electron transparent. Then in these areas, we can do TEM and really resolve the defect structures to tell us what kind of deformation mechanisms are activated. In this case, we'll have the one-to-one correlation of the deformation mechanism with the Schmidt factor crystal orientation in the material. And last, definitely not the least, is we do the orientation mapping and the strain mapping. When we talk about orientation mapping, especially for people who are from metallurgy as well as ceramics background, the first technique that comes to your mind usually is EBSD. EBSD stands for electron backscatter diffraction. The micrograph you see on the left is an example we did back at Hopkins on boron carbide. The sample was consolidated and you can see it's fairly dense. From the EBSD map, you can tell a lot of information. First, you can tell the crystal orientation as well as texture information. Each color here tells you the orientation of the crystal. If most of the grains, they have the same color, you know there's a strong texture. If most of the grains, they have a random color, you know there's no strong texture. Also, we can perform the face identification. One classical example is the duplex steel. Most of the steel we use nowadays, it has FCC and BCC crystal structures. Using EBSD, you can easily tell like where the FCC grains are, where the BCC grains are. We can also easily measure the grain size. We can look at the grain morphology. Some of the grains are equiaxed in this example, while other grains are elongated. And also we can look at the grain boundary characteristics. For example, we can look at regular grain boundaries. Those are the dark lines in the map. We can also look at the twin boundaries. Those are the red lines in the map. And most importantly, these images are pretty. However, for EBSD, there are some limitations. The first limitation is sample prep, especially before the age of ion milling. Sample prep is extremely challenging to give you like a good sample surface that you can do EBSD. Whoever have done EBSD will know how challenging that is. The second limitation is more intrinsic. It's governed by physics. In SEM, it doesn't matter how fine we tune the electron beam. What signals we're generating, those are the backscattered electrons. The interaction volume is way larger than the beam size. Even if we can tune the beam to a very fine probe, then the electrons will backscatter, and that interaction volume, the interaction size is a lot larger, so that degrades the resolution. For regular EBSD, the standard spatial resolution is 20 to 50 nanometers. That basically means even if you can tune your beam to 2 nanometers, 1 nanometer, still the interaction volume is a lot larger. In TEM, the advantage is the sample is not thick anymore, it's fairly thin. The sample thickness is finite. So when the electron beam passes through the specimen, there's still some scattering going on. There's some beam broadening going on, but not as bad as in EBSD. So we can dramatically improve the spatial resolution. On the TEM microscope at MIC, the spatial resolution, like the finest spot we can tune the beam to is about 3 nanometers. Considering some level of broadening, we can easily get 5 nanometer spatial resolution. Then how does that work? You have seen one slide from Robert. I'll just quickly go through that again. Using the PED system or the Nanomegas A* system, the beam rocks, and underneath we acquire the experimental diffraction data pixel by pixel. So the beam will actually rest on the specimen, and we collect the information pixel by pixel. From each pixel, we have the experimental data, that's the raw data. Then this information will be compared with the simulated diffraction pattern to give us 2 types of information. It will tell us the phase information, the crystal structure information, like whether it's FCC, BCC, or HCP. It will also tell us the orientation information. This example was done by Paul Rotman, a grad student in my advisor, Professor Kelvin Hamker's group. In this example, there was a slightly annealed deposited copper thin film. The scale bar down here is 100 nanometers. So you can see many grains you see here. Those are tens of nanometers in size, which is way beyond the resolution limits of EBSD. For many of the grains here in EBSD, it's just 1 pixel. If it's 1 pixel, you cannot tell whether it's there or it's just noise. Another thing to me is quite amazing is not only you can capture some of the nanotwins, like tens of nanometers in size, so these are nanotwins. Also, you can capture those super fine twins in this copper thin film. In our group, we also used this technique to solve some materials problems. So let me give you one example. The first example is we'll look at the shear bands in commercially pure titanium. Before going to the example, let's look at this animation. I guess all of us are old enough to use something called pencil. For younger generation, especially for kids nowadays, they use tablet. They don't really use a real pen to do writing anymore. The pencil will get dull after using for a while, and you need to sharpen the pencil. You put it in the sharpener, and a strip, like a chip, will come out. Now, imagine you replace that pencil with a metal rod and do the same thing, do the cutting, and a strip can also come out as well. That's exactly what you see here. What our collaborator, Professor Dinaka Sagapuram at Industrial Engineering did was he was cutting some titanium alloys, some titanium materials to form the chip you see. In titanium, the SEM image you're looking at here is a cross-section of the strip or the chip. So we're looking at this side of the metallic strip. What he did was he used some micro markers before deformation. All those are straight lines. After cutting, you see those shear bands. So outside the shear bands, the micro markers that are still more or less parallel to each other, but within the shear band, there's so much deformation going on. This is a polished sample then etched. Again, like between the shear bands, you can see fairly large grains, some deformation twins, but within the shear bands, the microstructure is so complicated to be resolved. Again, when Dinaka approached us, the first technique we applied was to use EBSD. In this case, this is the top view of the metal strip. So you're looking at the top. In this region, by the way, the work was really done by Dr. Xiaolong Ma, who was a postdoc in our group. Now he's a permanent staff in PNNL. When putting the sample in EBSD, we easily found there are shear bands. Then outside the shear bands, you see individual grains, and you see some deformation twins. But within the shear bands, EBSD cannot tell you anything. Then Xiaolong did some TEM. Using TEM, this is the shear band, and on both sides, these are the regions outside the shear bands. Looking at the regions outside the shear bands, you can see large grains, large crystals. There are some bending contours. You can see those spider web-like features. Those are bending contours, as well as some elastic strain stored in the material. When doing diffraction pattern, you see quite distinct spots. Tell us it's polycrystal, but not too bad. We see a few crystals here. But inside the shear band, it's very complicated. You can see individual nanoscale grains in the micrograph. When doing the diffraction pattern, you can see diffraction rings that tell us it's nanocrystalline in nature. So this is something we can tell from conventional TEM, but is that the case? In the similar area, we used A-star to look at the microstructure. Again, this is the PED bright field image. And within the shear band, you see those individual grains, quote unquote individual grains. But when looking at the orientation map, very surprising. What we saw was these individual, seemingly like individual grains, they actually belong to a giant grain, a giant parent grain. It's not only here, in many other regions, you can see they have large crystals. So what this tells us is those features which appears to be grains, those are not separated by large angle grain boundaries, not by conventional grain boundaries, rather they are separated by the low angle grain boundaries. Let me give you one analogy of what this means. The conventional view of looking at the nanocrystalline features, it's more like this. You have dinner rolls, and each dinner roll has its own orientation. It's kind of like random, or maybe it's textured, but it's separated by those large angle of misorientation. Then what we observed using A-star inside TEM was, instead of like getting random, most of the grains, most of the nanocrystals, they have a similar orientation. This is kind of like the Aloha rolls you buy from HEB, or the dinner rolls just out of the oven. Most of them, they have the same orientation. Coming back to this micrograph, remember in the previous slide, we did diffraction in the shear band region, and we showed indeed we see near continuous diffraction rings. If those are low angle grain boundaries, why we can see the like near continuous diffraction rings, then Xiaolong also did align scan to look at the misorientation. He looked at two types of misorientation, point to point and the point to origin. Point to point is looking at 2 to 1, 3 to 2, 4 to 3, 5 to 4. And it's indicated by the blue curve. In most of the cases, for point to point misorientation, it ranges from like 0 degree to 7 degrees. The second thing he looked at was the point to origin misorientation. Point to origin misorientation is 1 to 0, 2 to 0, 3 to 0, 4 to 0. And it's only about 500 nanometers, and the misorientation can be as large as 20 degrees. What this tells us is, although individual grains, individual sub-grain boundaries, that gives you a small angle of misorientation, but this effect stacks up. It will accumulate and eventually lead to a much larger misorientation, even in the same grain. Then you may wonder why this is important. Like, how does this teach us in terms of the processing as well as deformation of metallic systems? There are two implications to us. The first implication is in the shear band community, what people have been doing is they found this interesting. They thought those were nanograins, but to form those nanograins, they need a process called recrystallization. In order to have recrystallization, you need sufficient temperature, but the temperature measured during the shear band formation is not enough to activate recrystallization. What we have demonstrated here is there's no need to correct the adding another term to account for the missing temperature effect, because there's no conventional recrystallization going on. There's no need for the raise of temperature. The second thing is we can use this observation to explain some unsolved mystery in another branch of metallurgy called severe plastic deformation. People have been using severe plastic deformation to create those nanograins, but when looking at the strengthening effects, it's not as good. What we have demonstrated here is for some of the materials, maybe during HPT, during the high pressure torsion, severe plastic deformation, instead of creating the conventional grain boundaries, which are effective in terms of strengthening, we're creating those low angle grain boundaries, which are not as effective in terms of strengthening. So this is the orientation mapping part of my presentation. I'll move to the strain mapping part. For strain mapping, again, like for most people, the first technique is EBSD-based technique called kernel average misorientation. I took the example from Oxford Instruments. The micrograph you see here is EBSD map of a bent nickel tube. And on top, it's bent kind of this way. On top, there's tensile. It experiences like a tensile stress. Underneath, it experiences the compression stress. And in the center, there's no deformation. That's the neutral axis. So it shouldn't be any strain. This is exactly what people captured here. So using KEM, you can see on top, you see a lot of strain. There on the bottom, you see a lot of strain as well. And in the center, there's no strain at all. Then how does KEM work? The principle is very simple. To me, it's ingenious. In EBSD, we know the combined Euler angles of each individual pixel. So we can use this arrow to indicate the Euler angle or the combined Euler angle in the pixel. Then it will look at the orientation of the neighboring pixels as well. In this illustration, this is only the first nearest neighbor. In the software, usually by default, is the third nearest neighbor. In this case, the center pixel has the same orientation as the neighboring pixels, and it will be identified as strain-free. In this example here on the right, that's the pixel of interest. And around this pixel, the orientation is different. So the average Euler angle comparing to this will be different. And this will be strained, will be identified as a strained pixel. There are merits of this technique. It gives you good visualization of subgrain boundaries as well as strain distribution in the material. However, there are some limitations as well. The first limitation is intrinsic, is the spatial resolution limitation from EBSD. The second issue is it does not tell you whether it's elastic strain or plastic strain. The third limitation is there's no strain information embedded. Again, back to this example, we know on top is tensile. down the bottom is compression. But in both cases, they are green in color. They just they lit up. It doesn't tell us whether where it's tensile, where it's compressive. The work I'm going to present is actually not from my group. It was done by Paul Rotman, who was a PhD student in my advisor, Kelvin group. Now Paul is a faculty at University of Kentucky. In A-star, the idea, again, is from diffraction. In the real space, if we elastically stretch a material, in the reciprocal space, when looking at the compression, the diffraction pattern will be compressed in the same direction. And vice versa, if the material is elastically compressed, then the diffraction pattern will be stretched in the reciprocal space. In this case, it tells us like a number of informations. First, we have good spatial resolution. We are not limited by the spatial resolution of EPSD. The second is now we can easily tell the difference between elastic strain and the plastic strain. Using the Nanomegas A-star top spin system, what we are getting is the elastic strain. You may wonder where do we find the plastic strain. The plasticity is accommodated by either dislocations or deformation twins or phase transformation. And the third thing is in EBSD, TEM, we don't know the strain direction. Here, we can easily tell whether it's tensile or compression. We get the strain direction information. Robert has shown you an example of the electronics in semiconductor industry. My advisor, Kevin Hemke, he was asking now, like before people have demonstrated, they can do strain mapping in single crystal silicon. Can we try some more challenging systems? The example we looked at was the boron carbide sample. And in boron carbide sample, it's polycrystalline. And we speculate there will be residual strain at the grain boundaries. The first thing to do was to find a reference point to see the center, whether in the center we get a lot of strain or not. Can we use the center as the strain free area to give us a benchmark? So what Paul did was Paul put a box here, then looked at the strain information. Then he integrated the strain value along the y direction, then plotted against the x direction. This was what he got. This is the strain distribution. It's not too bad. If we look at the 2 sigma, look at the standard deviations indicated by the sigma, looking at the 2 sigma as the boundary, the strain sensitivity is within 0.05%. So what this tells us is anything within this window here, maybe it's just background noise, but anything outside the boundaries here, it will, well, confident, most likely it's real strain. And also if I draw attention to the value, the strain sensitivity, like by considering the 2 sigma, it's 0.05%. That's very, very small amount of strain. That's how sensitive this technique is able to achieve. Okay, now let's look at the grain boundary. We were lucky to find an area we have 2 grains having very similar orientation, very similar out of plane orientation, but it's rotated in plane. So it's more like a tilt boundary. What you see here, that's the out of plane orientation map, or IPF, inverse pole figure. They have similar color, but if we do the in-plane IPF, in-plane orientation mapping, they show different colors. And these are the crystal structures overlaid on the crystal orientation map. You can see the boron carbide can be viewed as hexagonal crystal structures. If we look at the c-axis of the orange grain and the c-axis of the blue grain, they're about 70 degrees apart. What Paul did was, first of all, he looked at the literature to study, to find out the information of the coefficient of thermal expansion, the CTE. For boron carbide, because it's hexagonal, so it's so anisotropic in terms of the physical properties. The a-axis, so this is the a-axis. During cooling, the a-axis shrinks less than the c-axis. So the c-axis will shrink more than the a-axis. Now let's construct a simple model, which was done by Paul. Let's just make the misorientation 90 degrees instead of 70 degrees to simplify the scenario. The grain on the left, the c-axis is pointing up. the grain on the right, the z-axis is pointing flat. Assuming the grains are free to contract during the cooling process in consolidation, the grain on the left will contract more along the y-axis. The grain on the right will contract more along the x-axis. But they are glued by the grain boundary. So they're not free to do this kind of like contraction. It will be something like this. This will be the end result. In this case, the grain on the left are stretched by the grain on the right. So it will be tensile residual strain. The grain on the right is trying to be compressed by the grain on the left. So there will be compressive residual stress. Let's have a look. Is that something we're seeing here? So in this model here, we have less contraction here and more contraction here. So that's small shrinkage, that's larger shrinkage. And by prediction, the grain on the left, we should see a compressive residual strain on the near the grain boundary. And this is the strain mapping information done by Paul. And this is the map. So inside the grain, it's really nice. There's nearly no residual strain at all. But as you approach the grain boundary, the value, the absolute value of the strain increased dramatically. And also it has like the near exponential shape. So this agreed very well to what we have predicted using a very simple model. Another thing I like to draw attention to is if you look at the shape, as I mentioned, it's like exponential shape. Using the elastic theory that agrees with that as well. So there are two actually there's only one takeaway message from my presentation. I hope through my presentation, I have demonstrated through two examples. One is titanium, another is boron carbide, that TEM-based orientation mapping and strain mapping, these are very powerful techniques to reveal microstructure, which was impossible or nearly impossible to reveal using conventional characterization techniques. The second thing I like to talk about is the path forward. Now at MIC, we have both the prototypes in situ heating holder. We also have the nanometers orientation strain mapping capabilities. So the next step for us to do is to combine these two techniques to generate new knowledge and new information. As the last slide, if you are interested in learning about the technique, we filmed a number of tutorials and you can check them out. There are 3 videos for now. The first video is to show you how to do data acquisition. Then the second video is to show you how to do the data reconstruction. And the third video is on data visualization. In the next few months, once we have a good system to study for strain mapping, we'll also film the strain mapping data acquisition as well as data analysis. That concludes my presentation. I'm happy to take any questions.
That was fantastic. Thank you so much, Kelvin. And really great motivation for using these instruments. I really appreciate it. Does anyone have any questions for Dr. Shi? I know that sometimes it's on Zoom calls, it's more challenging to get on and ask those questions. But I'm sure that Dr. Shi will be available if you have any follow-on questions. And just a reminder that we are going to be having a demonstration this afternoon using the A-Star. And before that, at 1:30, there will be a video tour of the MIC if you haven't been in to see it. But I think it should be a nice overview of the MIC. Again, you can always contact our staff if you have imaging needs that you're looking to fill either in the MIC or somewhere on campus. And then at 2 o'clock, we'll have the virtual demonstration of the A-Star, and that will be again on this same Zoom call. So we'll be closing the Zoom call over kind of the lunch period, and then we'll be back on at 1:30 for the tour and 2 o'clock for the demonstration. Let's see, Ashlyn, is there anything else that we need to cover? for people. I do want to thank again all of our speakers this morning. It was really fantastic and such a great overview of the technologies that we have in the MIC now. And thanks again to Dr. Shi for helping us or enabling us to be able to have these technologies installed on the TEM. We're really, really excited, and it's wonderful to see the results of the research in your presentation. So thank you so much.
Thank you.
Yeah. Ashlyn, do you have anything else?
I think that's it for me, as long as there's no more questions. We have plenty of time if anybody's got anything they'd like to ask. I think most of our staff is even on the call if you have another question while you're here.
Great. Well, we will stay on in case anybody wants to stick around and chat or ask a question. If the speakers are still on, then you can follow up with them on any questions you might